All right, chemistry, here we go. Let's talk about chapter 7, the specifics, for a little bit here. What does a chemical bond do? Why does a chemical bond form? What are the three types? Simply put, a chemical bond is going to hold two or more atoms together. Why does a chemical bond form? The answer is not stability. I know you're thinking of that, and that's part of it, of course. But why do atoms bond with each other? What are they trying to get? They're trying to get an, what is it? Starts with a vowel. They're trying to get an octet. Or, for a few of them, it's simply a what? Full, fancy word, starts with a V. You betcha, a full valence level. Now, the benefit, the byproduct of having a full outer level, having an octet, is that the atom will be more stable. And so that's why almost every atom does form a bond with somebody else. The three types, we've talked about two of them. You betcha. Ionic, covalent. The less well known is a metallic bond. We'll talk about him later. I think you saw this picture a long time ago, but we got to remember what's going on here. The nuclei hate each other. They're pushing away. The clouds hate each other. They're pushing away. But if the nucleus from atom A is attracted to the cloud from atom B strongly enough, and vice versa, nucleus B is attracted to cloud A, if the attractions are greater than the repulsions, the atoms will come together and they will bond. If the repulsions are greater, they will not. The attraction from the nucleus to the other cloud is what's going to determine if it's ionic or covalent. If the attraction is super duper strong, it's going to go ionic, and the electrons will be what? What's the big word? If the attraction is kind of strong, then we will merely share the electrons. But if it's really strong, we'll do what? We'll transfer those. Now here we go back again briefly. Why do we bond in the first place? We want to have a what? Full outer level. That will give us stability. Now here's the thing. If I am stable and I have a full outer shell, that's going to give me and my cloud, or allow me to have, a lower amount of potential energy. Not phys ed, not weights. So we bond, that lets me exist with a lower amount of energy, and that means that I've got a lot of extra energy that I don't need. So what do? I release it. I release energy when I bond with somebody. Fancy word for that. Been a long time since we talked about it. Starts with an E. And then what's that fancy word that means energy or heat? Thermic. What kind of thermic is this? When I let it go to the outside, dun dun dun, exothermic. When atoms bond, it's usually an exothermic reaction. On the flip side of the coin, if I want to take two things apart, when I break the bond, energy must be what? Taken in, absorbed, however you want to say it. And what is the opposite of exothermic? When energy is taken in, it is called an endothermic reaction. Here's our definition for ionic bonds again. Fancy one. It's the bond formed due to the big word, electrostatic attraction between ions. What does this mean? Opposites attract. The more common way to say or to define an ionic bond is say it is the bond formed when electrons are what? Transferred. And we've said that definition many times. Sodium, 1 valence. Chlorine, 7 valence. How could these two ever bond? Sodium wants to lose 1 electron. Chlorine wants to gain 1 electron. It's a perfect deal. But now sodium is positive 1. Chlorine has become negative 1. Electrostatic attraction. They are stuck together. Magnesium, oxygen, another perfect match. Transfer, transfer. But now, what do we get out of that? We get a +2 and a -2. So they would really be strongly held together. One last one, and then we move on here. Calcium, 2, chlorine, 7 valence. That ain't gonna work, is it? Because if calcium can't get rid of both, there's no point in doing this. So what has to happen here, does there have to be 2 chlorines if this is going to work? And that gives us with calcium, lost 2, chlorine, chlorine. And you think about 2 weeks ago, how did we write these formulas? Well, writing it that way we thought was silly, so we do what? Calcium, subscript. Because positives and negatives must always be dun dun dun. All that stuff makes sense now, doesn't it? Wow. That's a picture of salt. That's your salt crystal. Which is which? Who's the sodium? Who's the chlorine? Sodium will be the what? The big or the small? Small. Long ago, chapter 6, when you lose an electron, your cloud shrinks. Chlorine, gain an electron. When you gain an electron, anion, big cloud. Now, here's the trick. What's the formula for table salt? Sodium chloride. We know that it's 1 and 1. 1 positive, 1 negative. But the question here is, I'll go this one right here. We'll call him old Yeller. Who is Yeller bonded to? Is he bonded to the left, to the right, to the top, to the bottom? Is he bonded to the one behind him, the one out in front of here? And the answer is yes. He is bonded, he is pulled in all directions. But that would mean that the formula here is something like Na28Cl28 if we count all of them. And that would be a silly formula. So what do we always do with the formulas? Remember this from last chapter? We do what? We don't like big numbers. We always reduce. And then the last thing here, that's called a formula unit. You can make your own jokes with the abbreviation later. But a formula unit is the simplest. Simple means small in math. Smallest ratio of ions. And what do those ions have to give us? They have to give us balanced charges. So sodium chloride, 1, 1. That's the simplest ratio. Calcium chloride, +2, -1. Crisscross applesauce. Smallest ratio, 1 to 2. Now, what's a crystal lattice? Two big words that simply mean this is the three-dimensional arrangement of the ions. So the fancy picture on the previous page, that's the crystal lattice. What is lattice energy? This is a two-way street. It's the amount of energy needed to completely break apart the crystal lattice, or it's the opposite. It's the energy released when the crystal lattice forms.